In this video, I'll talk about a few key results that involve eigenvectors and eigenvalues. So the first theorem is that the eigenvalues of a triangular matrix are just the entries that are on the main diagonal. So this is true whether our matrix is upper triangular or lower triangular. So just as a brief review, remember a matrix is upper triangular. So it is upper, and I'll just abbreviate upper triangular, when the entries that are either on the main diagonal or above it can be anything, but the entries that are below that main diagonal are all 0. So that's upper triangular. A matrix is lower triangular if it's sort of inverted. So if the things that are on the main diagonal or below it can be anything, but the things that are above that main diagonal are all 0. So that is what a lower triangular matrix looks like. So when we have a matrix like either of those, then the eigenvalues are really easy to see. They end up just being the entries that are on this main diagonal. So on this main diagonal. So the proof of this is doable now. We can do it based off of what we know now, but it's easier in section 5.2 once we develop some additional tools. So we'll do it then. I just wanted to state this theorem now because it's useful when we see problems where we have a matrix that is triangular, so we can quickly identify what the eigenvalues are. But the actual proof we'll do it in the next section. Okay, and then the next theorem is that when a matrix is not invertible, that is true if and only if the matrix has 0 as an eigenvalue. Okay, so let's talk about the proof of this. Okay, so when lambda equals 0 is an eigenvalue of A, so lambda equals 0 is an eigenvalue of A, this is true if and only if the equation A times x equals 0 times x. So 0 is taking the role of the lambda here. It's an eigenvalue. So this equation needs to have a non-trivial solution. Because that non-trivial solution, whatever the x is, that will be an eigenvector. That corresponds to the eigenvalue 0. Okay, but the right-hand side simplifies. 0 times x is just the 0 vector. So this is saying, this is true if and only if A times x equals 0, equals the 0 vector, has a non-trivial solution. But if this homogeneous equation has a non-trivial solution, that means my matrix A has a free variable. And that would mean that A is not invertible. Let's put not in red. A is not invertible. And that concludes the proof. So this proof is actually pretty quick. All right, so let's do one more theorem and then state its proof. Okay, so this is the following. So if V1 up until Vr are eigenvectors of my n by n matrix A, corresponding to distinct eigenvalues. So distinct means that they're corresponding to different eigenvalues. So lambda 1 up until lambda r. So no two of these lambdas, these eigenvalues, are the same. They're distinct. Then it turns out that their corresponding eigenvectors, v1 up until vr, that is a linearly independent set. Okay, so this is a really important result that's going to be relevant to us in this chapter. So this one I want to prove. And the proof of this is done by contradiction. So we'll prove this by contradiction. And we've seen proof by contradictions before. In a proof by contradiction, we begin by assuming the opposite of what we want to show, and then try to get a contradiction. Try to show that that leads to an impossibility. So assume, for the sake of contradiction, that, so what's the opposite of what we want to show? I want to show these vectors are linearly independent, So let's assume that they are linearly dependent. Assume that the set V1 up until VR is linearly dependent. Okay. Then, well, if my set of vectors is linearly dependent, that means one of them, at least one of them, is a linear combination of the vectors that precede it. Okay, so I'm going to write this in the following way. Let's let Vk be such a vector. So let's let Vk be the first vector in this list that is a linear combination of the preceding and I'm going to add one more word into this, preceding independent. Let's switch it back to blue, vectors. Okay, so let me write that down. Okay, so what that would mean is that Vk, there's some vector Vk in that list, that's going to be a linear combination of the vectors before that. So C1 V1 plus plus Ck minus 1 times Vk minus 1. So Vk is a linear combination of the vectors before it. And we're also saying that the set of vectors V1 up until Vk minus 1, that this is linearly independent. Okay, so this statement right here in gray, that the vectors V1 up until Vk minus 1, that set is linearly independent. This might look a little strange, because usually when we've done proofs involving a bunch of vectors being linearly dependent, and we've said that, oh, that means one of the vectors is a linear combination of the others, or a linear combination of the ones before it, we haven't said something like this. But it turns out we can, if we need to. If my set of vectors is linearly dependent, conceptually what that means is, if I start looking at this list, like V1, and then V2, and then V3, down the list, initially, our vectors are linearly independent, at least the ones sort of at the beginning, considered on their own. Like if I look at just the vector V1 by itself, as long as that's not 0, that set is linearly independent. And then if I look at the set that has V1 and V2 in it, like maybe it's linearly independent, but if it's not linearly independent, well, that would mean that the second vector, V2, is a multiple of the first. And I could keep going like this. What I'm basically doing is I keep going like this until I find the first vector that is a linear combination of the ones before it. And I'm saying that that vector is Vk. And if that was the first vector that's a linear combination of the preceding vectors, that means those preceding vectors had to be linearly independent. Okay, so this equation right here, I'm going to label this as equation 1. There's going to be a few equations in this proof, so I'm going to keep track of them with numbers. Okay, so now what I'm going to do is, I want to be able to utilize the fact that we know what the eigenvalues of these vectors are. And to utilize that fact, I'm going to multiply both sides by a. I'll do a times whatever, so I'll multiply by a on the left. So doing that, what we get is, we get a times Vk on the left. On the right hand side, when I multiply by a, I can distribute a to each of these terms. So I can distribute it here, and distribute it here, and so on, and then use the property of linearity to say that, oh, this is C1 times a V1 plus plus Ck minus 1 times a times Vk minus 1. Okay, so now let's utilize the fact that we know what the eigenvalues are. So because we know what the eigenvalues are, a times Vk is going to be lambda k times Vk. So here I'm utilizing the fact that a times Vk equals lambda times Vk, and that's because Vk is an eigenvector. It's an eigenvector, whoops, sorry, forgot to write lambda k, with eigenvalue lambda k. If I do the same type of thing on the right hand side, I'll get C1 times, and then I'll get lambda 1 v1, because lambda 1 v1 is what a times v1 is, plus plus ck minus 1, and then a times vk minus 1 is its eigenvalue, which is lambda k minus 1, times that vector, vk minus 1. So I can only rewrite these a times vi's as like this eigenvalue times vi, because I know that these vi's are eigenvectors. If they weren't eigenvectors, I couldn't rewrite them like this. Okay, so this equation right here, let's label this equation 2. Okay, so now I'm going to do one other thing. Now, I'm going to go back to equation 1, and let's multiply both sides by something else. Let's multiply both sides of equation 1 by the eigenvalue lambda k. So I'll do that and then I'll talk about why it's useful. So I get lambda k times vk on the left. On the right hand side I'll get c1 lambda k times v1 plus plus ck minus 1 lambda k times vk minus 1. And this I'll call equation 3. So equation 3. So what I want to notice is that the left hand side of equation 2 and of equation 3 are exactly the same. So if we subtract them, that left hand side is going to become 0. So if we do that, so I'll do equation 2 minus equation 3, so in that order. And if I do that, I get the 0 vector on the left. On the right hand side, I will get, so I notice that both of these terms have a c1, so I can factor that out, and both of them have a v1, so I can factor that out. And I'll get c1 times lambda 1 minus lambda k times v1 plus plus, and then going to the last terms that I'm going to subtract, they both have ck minus 1 in common and a vk minus 1 in common, so we'll be able to factor those out. I'll get ck minus 1 times lambda k minus 1 minus lambda k times the vector vk minus 1. Okay, so at this point there are a couple of things that I want to notice about this. So the first is that each of these terms that I'm underlining, these difference in eigenvalues, these are all not equal to 0. They're not equal to 0 because the eigenvalues are all supposed to be distinct. So this is since the eigenvalues, the lambda i's, are distinct. Okay, so that's nice. That's nice that they're all non-zero. The other part that I want to note about this is that since the vectors v1 up to vk minus 1, since this set of vectors is linearly independent, and what I have here is I have a linear combination of these linearly independent vectors, v1 up until vk minus 1, that equals 0, because remember, it equals 0 on the other side. That means the only solution is supposed to be the trivial solution. So because these green terms that I've sort of underlined, all of these things are not 0 because the eigenvalues are distinct. The only way to make the solution the trivial solution is if we make all the c terms equal 0. So at this point, we can say that c1 up until ck minus 1, all of those have to be 0, because that's the only way we're going to make this the trivial solution. Okay, so why, or what can we do with this? What can we do now that we know that c1 up until ck minus 1, all of those are 0? So what I'm going to do with that is I'm going to substitute that back into equation 1. So if we plug this back into equation 1, we get that the vector vk equals 0 v1 plus plus 0 vk minus 1. But that just equals 0. So we know that vk equals 0, but an eigenvector and Vk is supposed to be an eigenvector, but an eigenvector is non-zero. An eigenvector is not supposed to be 0. So that is our contradiction. An eigenvector is not supposed to be 0, but we got that this eigenvector is 0. So therefore, let's zoom it back in and write down our conclusion. So therefore, our assumption that the set of vectors v1, comma, da, 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 up until vr is linearly dependent, that assumption was wrong. Let's write wrong in red, was wrong. And if our assumption was wrong, that means that v1 up until vr, those eigenvectors, that set of eigenvectors is linearly independent, and that is what we wanted to show. So that concludes our proof.